Okay, so today we're going to be talking about conditional probability. This is also known as dependent probability, and it's determined after another event has already occurred. So the way that we write this is the probability of event A given event B. That's what this little vertical bar means. Given. So B happens first, and then A happens. Okay, that's the way that this works. And the way that we write it out is it's the probability of A within that B already occurring divided by the probability of B. With these, I'm going to have you guys make tree diagrams because to me they make the most sense and they're the easiest visual aid to you to do. We'll still use the formula, but I'll incorporate a tree diagram with that to kind of show you what I'm talking about. Okay, so here we have an example that is, completely made up. During a purely hypothetical pandemic, 35% of a school students have the disease. Of those with the disease, 90% have a high temperature. However, a high temp is also possible for students without the disease. In fact, the school nurse estimates that 12% of students without the disease still have a high temp. All right, before we do anything, what I want us to do is make a tree diagram. Okay, so, and I didn't leave space here on my paper, so we'll just kind of go like this. I don't know if this will work or not. Okay. So with a tree diagram, you obviously have your first branch going on. And in this case, you either have students with the disease or they're healthy. Okay, so disease or healthy. All right. And then we fill in the blank. So 35%, 0.35 have the disease, 0.65 therefore are healthy. Okay, each branch has to add up to 1. Now, you've got students with the disease that either have a high temp or a normal temp, and then you've got students that are healthy that have a high temp or are a normal temp. Okay, and then again, from the information in the problem, fill in the blank. With the disease, 90% have a high temp. So along the disease branch, 90% have a high temp, only 10% have a normal temp. Okay, but the healthy kids, okay, 12% of students without the disease still have a high temp. So 12% of the healthy kids still have a high temp, meaning 88% of the healthy kids have a normal temp. Okay, so again, before you do anything, you have to figure out the probabilities going down, and you're going to multiply those down. So 0.35 times 0.9 will determine of the entire population how many have the disease with a high temp. So 0.35 times 0.9, 0.315. Okay, 0.35 times 0.1, just move the decimal point over 1, you get 0.035. Okay, the healthy 0.65 times 0.12, so healthy kids with a high temp, 0.078, and 0.65 times 0.88 gives you the healthy kids with a normal temp. Okay, couple notes here. Notice how along this branch, 0.315 and 0.035, that should add up to 0.35. If you do your math correctly, these two numbers on this branch should add up to this probability up here. Same with this, should add up to 0.65. Okay, now this is the probability tree that we have. All right, so when we are using it, all right, it's actually pretty easy to do. First one, determine the probability that a student has a high temperature. Nothing conditional about this. How many kids have the high temp? Okay, well, you've got two branches with the high temp. You've got this branch, and you've got this branch. So all you have to do there is add those two together. So 0.315 plus 0.078 0.393. So the probability that a student has a high temp is about 39.3%. Okay, now we get to a conditional probability question. Determine the probability that a student has the disease given that they have a high temp. Okay, so the high temperature has to happen first. All right, so again, using the formula that we said, it's going to be the probability of the disease within the high temp, or the disease with a high temp. Maybe I should just say that. That will make more sense. Over the probability of a high temp. Okay. Well, the probability of a high temp, we actually just figured it out in the last problem, so it's 0.393. The probability of the disease with the high temp, well, that's this branch right here. That's the end of this branch right here, 0.315. Okay, so then you just divide those out. 0.315 divided by 0.393. And just go ahead and round to 3 decimal places, 802. So what this says is about 80.2% of students that have a high temperature have the disease. Okay, so given you just take a random sample of kids that have high temperatures, have fevers, whatever, according to this, 80% of them are going to have the disease, about. Okay. Let's do another example together. This one's a little less, relevant, maybe. I don't know. Suppose that in a given population, 60% of the females live to age 75 or older, while only 42% of the males live 75 plus years. If the population is 52% female, what is the probability that a 75-year-old person is female? Okay, ignore the question. Ignore the question right now. We have to draw our tree diagram first. Now, be careful. What comes first? Well, if you read the question, it might say, 75 or older or less than 75. That's not right. What comes first? Male or female? Okay, that's going to come first. All right, 52% is female, so 0.52 on the female branch means 0.48 on the male branch. Okay, that comes first. Then we determine whether they are going to live 75 plus years or less than 75 years. And I get that I'm mixing up my math symbols here, but that's okay. All right, so now fill in the percentages for these ones, okay? 60% of females live 75 plus. So 75 plus on the female branch is 0.6, which means 0.4 on the other branch. Only 42% of the males live 75 plus years, so 0.42 and 0.58. Okay, so then finishing the branches out, 0.48 times 0.42, it's the percentage of the entire population that are males that are 75 plus. Okay, and then 0.48 times 0.58. Males not 75. Kind of running out of room. 0.52 times 0.6. Just change colors there. 0.312. And then 0.52 times 0.4 is 0.208. Oh, that's ugly. All right. Now that we've got the probabilities all figured out, look at the question. What is the probability that a 75-year-old person is female? Again, these can be kind of tricky to understand what they are saying. What is the given? The given is that they're 75. Okay, so probability that given they are 75 plus, what is the probability that they are female? Okay, so again, using our formula, that would be the probability of the female with 75 plus divided by the probability of 75 plus. Always with these problems, with these tree diagrams, the denominator, you have to add a couple things together. Okay, because as we see here, you've got two branches that are 75 plus. So this is going to be your denominator right there. So you add those two numbers together, 0.2016 plus 0.312. That becomes your denominator, 5136. And then the females with 75 plus is the 0.312. And then you just divide those out. 0.607. So about 61% of those 75-year-olds are female. That's what we're trying to get with this particular problem. Okay.